Imagine standing on a quiet pier in January 1943, looking at a brand new vessel that represents the pinnacle of industrial might. The ship is the SS Schenectady, and it has just returned from its sea trials. It is sitting perfectly still in the calm waters of Swan Island. Then, without warning, a sound like a heavy artillery blast echoes across the shipyard. The hull of the ship suddenly tears open from the deck down to the keel. There was no impact, no external force, and no obvious reason for the steel to behave this way. This moment is one of the most significant puzzles in the history of forensic engineering. To understand why the Liberty ships were breaking, we have to look at the transition from old-world craftsmanship to mass production. During the early 1940s, the demand for cargo vessels was so high that traditional shipbuilding methods were too slow. The solution was the Liberty ship, a design built for speed of assembly. The primary shift was moving from riveting to welding. In a riveted ship, every plate is an individual unit held together by thousands of steel pins. If a crack starts in one plate, it usually stops when it reaches the edge of that plate, because there is no continuous path for the crack to follow. But a welded ship is essentially one single, continuous piece of steel. This creates a structural environment where a tiny flaw can travel through the entire vessel, like a tear in a piece of fabric. The evidence points toward a specific material behavior that was not fully understood at the time: the ductile-to-brittle transition. Most of us think of steel as a tough, flexible material. Under normal conditions, steel is ductile, meaning it will stretch and deform before it finally breaks. However, as the temperature drops, certain types of steel reach a point where they lose this flexibility. They become brittle, behaving more like glass or cast iron than the resilient metal we expect. During the war, these ships were frequently operating in the North Atlantic, where the water and air temperatures were near freezing. The steel used in these hulls was high in sulfur and low in manganese, a chemical composition that made the transition temperature much higher than it should have been. When the metal got cold, it didn't need a massive impact to fail. It just needed a point of concentrated stress. This leads us to the component level of the failure. If you look at the pencil sketches of the deck plans, you see the hatch openings where cargo is loaded. In the original Liberty design, these hatches were perfectly square. In engineering, a sharp 90-degree corner is known as a stress raiser. It is a location where the internal forces of the structure are concentrated into a very small area. The evidence suggests that nearly every major fracture started at these square corners. A tiny microscopic nick in the weld, combined with the extreme cold and the stress concentration of the square corner, created the perfect conditions for a fracture to initiate. Because the ship was welded, that fracture had a clear path to run. It could race down the side of the hull at speeds of several thousand feet per second. The common view at the time was that the welding work was simply poor, or that the rapid pace of production had led to negligence. While some welds were indeed rushed, the deeper issue was the system pressure of the era. The design trade-offs favored speed over the nuance of fracture mechanics, a field that was still in its infancy. We were building ships faster than we understood the materials we were using. The missing angle in the initial investigations was the role of notch toughness. Engineers eventually realized that they needed to test how the steel reacted to a sudden impact when a notch or flaw was present. This led to the standard use of the Charpy V-notch test, which is still a cornerstone of material science today. To solve the problem on the existing fleet, engineers had to think like surgeons. They began rounding the corners of the hatches to distribute the stress more evenly. They also installed what are known as crack arresters. These were long strips of steel, often riveted instead of welded, that acted as physical barriers. If a crack started to run across the deck, it would hit the riveted seam and lose its energy, preventing the ship from splitting entirely. The lesson of the Liberty ships is a fundamental one for any designer or builder. It reminds us that a system is only as reliable as its most vulnerable transition point. It taught us that the environment in which a structure operates is just as important as the loads it is designed to carry. We learned that a change in assembly method, like moving from rivets to welds, requires a complete rethink of how forces move through a material. Today, every bridge, skyscraper, and container ship owes a debt to the forensic analysis of those fractured hulls in the 1940s. We no longer just look at the strength of our materials. We look at their toughness and their ability to resist the spread of a flaw. The quiet snapping of the Schenectady was the sound of a new era of engineering being born, one where we respect the hidden boundaries of the materials that hold our world together. If you find these deep dives into the logic of how things fail interesting, consider following along for more case files. Let me know in the comments if there is a specific structural mystery you would like to see analyzed through this lens.